So, question 1. The quadratic expression f of x equal ax squared plus 12x plus b is divisible by x minus 3 and has a remainder of minus 27 when divided by x plus 6. So, x minus 3 is a factor since it's divisible by 3. So f of 3 give us the remainder, which is 0. It's a factor, so there is no remainder, right? So f of 3 is equal to 0. And the function has a remainder of minus 27 when divided by x plus 6, which means that f of minus 6 equal to the remainder, which is minus 27. So it's a combination of the remainder and the factor theorem. So now in that quadratic expression, we're going to replace x with 3, and then the other one we're going to replace x with minus 6. So let's first replace x with positive 3. So ax squared becomes a times 3 squared, 12x, 12 times 3, plus b. And that's equal to 0. In the second equation, replace x with minus 6, so ax squared becomes a times minus 6 squared, plus 12 times 6, 12 times minus 6, plus b, equal to 0. So we have a pair of simultaneous equations which we need to solve. So let's simplify the top one. 3 squared is 9. So 9a, 12 times 3, that's 36. Plus b equal to 0. The other equation, 36a, remember negative 6 squared, that's positive 36, right? And 12 times minus 6, that's minus 72. Plus b is equal to minus 27. And I recognize that we have positive b in both equations, so we can subtract, and that would eliminate the b. So we subtract by saying term above minus term below. So 9a minus 36a, that's minus 27a. 36 minus minus 72, that's 108. b minus b is 0. And then 0 minus minus 27. It's positive 27. So we solve this equation. Divide both sides by minus 27. And a is positive 3. Now this value for a, we can solve it into any one of the equation. Let's use equation. Let's use the first equation, which is 9a plus 36 plus b. Let's use equation 1. So substitute a equal 3 into equation 1. We get 9 times a, 9 times 3. Plus 36 plus b equal to 0. We solve this equation. 9 times 3 is 27, 27, 36, that's 63. So 63 plus b equals 0, so b is minus 63, right? So a is 3 and b is minus 63, so problem solved. Next, Hence determine the factors of f. Well, the other factors of f back, because we know x minus 3 is a factor. So we want the other factors, right? So remember a was 3 and remember b was minus 63. So we know that x minus 3 is a factor. So we can use factorization to get the other factor. So to get the 3x squared, the first term in the other bracket would have to be 3x. And to get minus 63, the second term in the bracket there would have to be minus 21, right? And you can always positive 21, sorry, and you can always check by expanding the bracket. You should get 3x squared plus 12x minus 63 if the bracket is expanded, right? The 3x plus 21, notice we can factorize further and extract positive 3 there. So we're left with x plus 7, which means the other factors would be x plus 7 and 3, right? Or we could use synthetic division, or we could use long division. If we're using long division, x minus 3 into 3x squared plus 12x minus 63. That's another way you could get the other factors. X into 3x squared, that's 3x. 3x times x minus 3. You get 3x squared minus 9x. Now we subtract. We will be left with positive 21x, because 12 minus 9. So left with 21x, and bring forward minus 63. So we say x into 21x, that's 21. And then 21 times x minus 3. We get 21x minus 63. And if we subtract, we get 0, so there's no remainder, which proves that x minus 3 is a factor. Now we have the quotient here, which is the other factor, 3x plus 21. Notice that x minus 3 times 3x plus 21 would give you 3x squared plus 12x minus 63, right? So we know 3x plus 21 is a factor, but can be further factorized and we can extract 3. So that's another way we still get the other factors to be 3 and x plus 7. Because that's what 3x plus 21 is when factorized. We have a absolute value inequality here. Modulus inequality. 3x squared, modulus of 3x squared is less than or equal, modulus of 3x minus 4 is less than or equal to 6. Alright, so we can write this, we can take one of two approaches. We can let the 3x minus 4 less than or equal to 6, or we can say 3x minus 4 is greater than minus 6, greater than or equal to minus 6. Or we can let 3x minus 4 be less than or equal to 6, and we're saying the exact same thing, greater than or equal to minus 6. And less than or equal to 6, positive. And of course we can solve for x by first. Yes, so we're circling there. You can solve those separately and you'll have your solution. Or we can solve for x there. So we can add 4 to each section. That would get rid of the minus 4. Or so we end up with minus 2 less than or equal to positive 3x. 6 plus 4, that's 10. And then to get rid of the 3, we can divide each section by 3. So we have a solution there. X is between, or we say it's less than 10 over 3, but greater than minus 2/3. Or we solve those separately, what we box up, and we still have our solution. Next. So we have a binary operation there. And we're told A asterisk b is equal to ab over 2. We are asked to prove that the operation is commutative, and if it's commutative, then we know the order is not important. So if it's commutative, a asterisk b is equal to b asterisk a, right? So if commutative, then the order is not important. So we are given with a asterisk b, we are told it's equal to ab over 2. So we need now to find b asterisk a and see if it's the same thing. So we take the product, put it over 2. That's what the instructions are. Take the product of the two values, b and a. Put it over 2. Now we ask ourselves, is ab over 2 the same as ba over 2? Yes. So the operation is commutative. So we're using induction to prove that 5 to the power of n minus 1 is always divisible by 4, so long as n is a natural number. N belongs to the set of natural numbers, right? So we're going to go through the 3 basic induction steps. So we're going to start with showing that the statement is true when n is equal to 1. And when n is equal to 1, 5 to the n becomes 5 to the power of 1, right? Minus 1. That's 5 minus 1, which is 4. And obviously 4 is divisible by 4, right? So it's true for n equal to 1. Now step 2, we assume true for n equal to k. And of course we define k. K belongs to the set of natural numbers. So 5 to the power of k minus 1. We're assuming that this is divisible by 4, which means it can be written as 4 times a value. Remember, when 4 can go into a number, it means that number can be written as 4 times a natural number. We use p, where p belongs to the set of natural number. Alright, so we assume that 5 to the power of k minus 1 is equal to 4 times some value, 4 times some random value, since it's divisible by 4. Now the third and final step is to show it's true for when n equal to k plus 1. Alright, so 5 to the n minus 1 becomes 5 to the power of k plus 1. And then minus 1. We need to show that this expression is divisible by 4. Let's rewrite the expression. Using indices, 5 to the power of k plus 1 can be rewritten as 5 times 5 to the power of k. And then we have our minus 1 outside there. Now 5 to the power of k, notice in the step above. What's in the step above there? 5 to the power of k minus 1 equal to 4p, which means that 5 to the power of k is equal to 4p plus 1. If you add 1 to both sides, you will get 5 to the power of k equal to 4p plus 1. So we can do some transposing there, and then we rewrite the 5 to the power of k as 4p plus 1. And then we put our minus 1. Expand our bracket. 5 times 4p, that's 20p. And 5 times 1, that's 5. And then we end up with 20p plus 4. And we can factor out 4. If we can factor out 4, it means it's divisible by 4, right? So notice we have rewritten the 5 to the power of k plus 1 minus 1 as 4 into 5p plus 1. And the fact that we can rewrite the expression there as 4 times a value, it means that 5 to the power of k plus 1 minus 1 is divisible by 4. Hence, divisible by 4. Hence, true for n equal k plus 1. Hence, true for all natural numbers. So, in other words, what we set out to prove, 5 to the power of n minus 1 is always divisible by 4, as long as n is a natural number. Next problem. So we have a function x squared minus x. We have to show it's a one-to-one or injective function. Notice above we are told that the domain of this function, all the possible x values, are positive. Well, they're actually 1 or more. All the positive x values are 1 and above. So we want to prove the function is injective. Remember, if a function is injective, then we can let f of a equal f of b, and then if injective, a should be equal to b. So let's find f of a now. F of a is a squared minus a, and f of b is b squared minus b. So we can group the squares. So we have a squared minus b squared. And we can group everything else. So we have a minus b on the other side. Now we can factorize difference of squares there. That's a minus b, a plus b equal a minus b. We can divide both sides by a minus b. And we are left with a plus b equal to 1. Now, is it possible for a plus b is equal to 1? Notice, remember that the values have to be 1 or more. The values have to be 1 or more. In other words, the lowest value has to be 1. So if a is 1 and b is 1, then 1 plus 1. Alright? So a plus b equal to 1 is not possible. It's not a possibility. Hence, a plus b equal to 1 is not a possible solution. Because remember, we are told that the x values, the domain, have to be 1 or more. So that's not possible. So we X that out. Let's try a different approach here. Because we're to show that it's injective or one-to-one. So we're supposed to get a equal to b somewhere. So let's go again. So again, we factorize difference of two squares. So we group everything on the left hand side. So a become negative a, negative b become positive b. And we factorize, we can factor out minus 1. And in the bracket, we have a minus b equal to 0. So notice a minus b is a common factor. So we factor out a minus b. And then we factor in the first term there, we'll be left with a plus b. And in the other term there, we'll be left with minus 1. So equate both brackets to 0. Maybe this is what we should have done in the first place. Notice we still get a plus b equal to 1. And which we say is not possible. Or a minus b equal to 0, we solve that, a is equal to b, right? So a is equal to b is a solution, which means the function is injective. Determine the inverse of the function f. So we let y be equal to 3x plus 1. Interchange x and y. And then we solve for y. And whatever we get for y, that's our inverse function, right? So f inverse would be x minus 1 upon 3. Now we are asked for f inverse of g. Now there is f inverse. Remember f inverse was x minus 1 over 3, right? So f inverse x is x minus 1 over 3. And g of x, e to the 3x. So f inverse g would be f inverse e to the 3 of x, right? Because g is e to the 3 of x. We sub it into the inverse. Replace x with e to the 3x. And we end up with that. Solve the equation. Now we have an exponential equation there. We should recognize that 81 can be written as 9 square. So 4 over 81, so it's 4 over 9 square to the power of x. So 4 over 9 to the power of 2x, right? Is equal to 0. So now to get rid of the fractions, we can multiply each term by the LCM here, which is 9 to the power of 2x. So 9 to the power of 2x times each term. Notice in that term, indices you're dividing, in the middle term there you're dividing, so you can, same base 9, so you can subtract power. So we have 4 and then 9 to the power of 2x, so that will become 9 to the power of 2x minus x, so it will become 9 to the power of x, right? So we subtract the powers, we get that, and then 9 to the power of 2x into itself, we're left with just 4. And 0 times anything is 0. So we let 9 to the power of x equal to y, we get a quadratic. So 9 to the power of 2x, so that would be y squared. 4 times y minus 4. So we have a quadratic we can solve by factorization. Notice AC is minus 12. So we think of two numbers that add to give minus 12, that multiply to give minus 12 and add to give minus 4. And those values will be negative 6 and 2, right? So we rewrite the 4y as minus 6y plus 2y. And then we factor by groups. So the first pair, 3y into y minus 2. The second pair, positive 2 into y minus 2. So we have our brackets and then we equate both brackets to 0 and solve, right? So y is 2, y is negative 2/3. So recall that 9 to the x equal to y, so 9 to the x equal to 2, and 9 to the x equal negative 2/3. So of course we're going to log both sides, take the natural log of both sides. Solve, so ln 9 to the power of x equal ln 2. In the other equation, if we log both sides, notice the log of a negative number that's undefined. Alright, so that's not possible. So the other will show that out. Because the log of a negative number, that value doesn't exist. So remember law logarithm that x to the power of 9 there, we can put it at the front. So x ln 9 equal ln 2, divide both sides by ln 9, so to get the x by itself, ln 9 divided into itself give us 1, so the solution is ln 2 over ln 9. That's our solution that we're circling there. Let the roots of the equation 2x cubed minus 5x squared plus 4x plus 6 equal to 0. Let they be alpha, beta, and gamma, right? So a is the coefficient of the 2x cubed, b, coefficient of the x squared, c of the x, and the constant, we call it d. That's 6. State the values of the sum of the roots. The sum of the roots, we have an equation for that, standard equation for that. We have an equation for the product and the product of the sum of the products. So the sum of the roots, the three roots there is negative b over a. Is 2, so that's 5 over 2. The product of the roots, that's negative d over a. Which is minus 6 over 2, right? And that's negative 3. And then this expression where you have the product of all the possible pairs of the roots, and we sum them. We have a standard value for that also. And that's c over a. And c is 4. So 4 over 2, 2. Hence, or otherwise determine the equation with roots alpha square, beta square, and gamma square. Now, if alpha square is a root, then we can have x minus alpha square. And if beta square is a root, we have x minus beta square. And if gamma square is a root, we have x minus gamma square equal to 0. Notice if you equate each of those brackets and solve, you get the roots. X equal alpha square, x equal beta square, x equal gamma square. Now we can expand these brackets here. Let's expand the first two brackets. You'll end up with x times x square, and then the middle term will be x, and you'll have alpha square plus beta square there. And the final term will be alpha square times beta square, right? Times the final bracket there, x minus gamma square. Alright, let's expand again. So now we just have two brackets, right? So x squared times x, that's x cubed. X squared times gamma square, that's x squared gamma square. And then we take that second term now and multiply it by x minus gamma square. So we get x squared and our alpha square plus gamma square, right? Now times that term by the minus gamma square. The middle term in the first bracket times x minus gamma square. And the second to last term, we have alpha square beta square times x, and the final term we have alpha square, negative alpha square beta square gamma square equal to 0. Now see if we can find the coefficients now. Now let's deal with the last term, alpha square beta square gamma square. Remember what was the product? What was alpha beta gamma equal to? Alpha beta gamma was equal to minus 3. If we square both sides, then the value of alpha square beta square gamma square would be 9. So that value will replace it with 9. That's a constant. Negative 9. Let's now try to get the coefficient for the x square. Notice that term, if you show the rewrite, let's factor out. Let's factor x square. You'll get gamma square. And you'll get alpha square plus beta square. What is that? Gamma square plus alpha square plus beta square. How do we find that? The question gave us a hint. Notice we are told that alpha square plus beta square plus gamma square is equal to the sum alpha plus beta plus gamma square, which we have that value. Remember, we have that value. And the bracket alpha beta plus gamma plus alpha gamma plus beta gamma, we have that also. The sum of the roots, we have that alpha plus beta plus gamma, that was 5 over 2, right? And what's in the bracket now was 2. Alright, so that's 2, and that was 5 over 2 squared, so that's 25 over 4 minus 2 times 2, right, which is 4. So 25 over 4 minus 16 over 4. That's what 4 is, right? 16 over 4. So 25 minus 16, that's 9. So 9 over 4. So the coefficient for the x squared is 9 over 4. Now the last thing we want now is the coefficient for the x. What's the coefficient for the x? There it is. Let's just make some space and rewrite the x. Coefficient for the x was alpha square, beta square, and that term should be positive, by the way. Minus x gamma square. It should be positive x gamma square, yes. So positive gamma square into alpha square plus beta square, right? Notice we get some help here. That's what we have there. So we're told that's equal to, and we have all of those values. That was 2, so 2 square 4. And then 2 times alpha beta gamma, that's minus 2. Alpha beta gamma was what? Minus 3. And the sum, alpha plus beta plus gamma, that was what, 5 over 2? So that's 4, and it should be plus, because minus 2 times minus 3, that's positive 6. Positive 6 times 5 over 2, that's positive 9. So it should be 4 plus 15. So 4 plus 15, which would be 19. Should be 19x. Let me just change that. Change that. Should be actually 4 plus 15. So the coefficient for the x should be 19. All right, now we have a trig problem. Now recall that we have a Pythagorean identity. 1 plus tan squared theta is equal to sec squared theta. So the tan squared theta in the equation there, the tan squared theta, we can replace tan squared theta with sec squared theta minus 1. And we can do that based on that identity. We transpose tan squared theta is sec squared theta minus 1. So in this equation, we can replace the tan squared theta to make all the terms sec, right? Or sec square. So the tan square, we replace with sec squared theta minus 1. And so we can group everything on the right hand side, right? Since we have a quadratic. So we have sec square and 2 sec square. And then 5 sec theta become minus 5 sec theta. And minus 1, that's minus 2. So we group the sec square, we get 3 sec square minus 5 sec theta. We have a quadratic, and as we know to factorize a quadratic, you want two terms that add to give the middle term and then multiply to give AC, which is minus 6. That's minus 6 and 1, right? So we can rewrite minus 5 sec theta as minus 6 theta plus 1 sec theta. And we put back the minus 2. And then now we factor by groups, right? So we factor by group. So 3 sec theta is a common factor in the first group and 1 in the other group. So we equate both brackets to 0. And then we solve for sec theta in each equation. Now if sec theta is, recall that sec is 1 over cos. Alright? So sec theta is 1 over cos theta. 2 is 2 over 1, right? So to get the cos theta, we can reciprocate. So cos theta would be equal to half, right? So we reciprocate both sides. Here, 3 sec theta is negative 1. So sec theta is negative a third. And remember, sec is 1 over cos, right? So reciprocate that, we get cos. And then reciprocate that, we get minus 3. Now cos theta, can cos theta be negative 3? No, remember cos theta always fall between 1 and negative 1. Remember the largest possible value for sin theta or cos theta is 1. And the smallest possible value for both cos theta and sin theta is negative 1. So cos theta always lies between 1 and negative 1, including 1 and negative 1. So cos theta is a half is our only equation we're working with. Now what do you cos to get a half? Now 60. You can use a calculator, shift. So theta would be equal to 60 degrees. And if you want to convert 60 degrees to radians, you multiply it by pi over 180. If you want to write your answer in radians, that's 60 degrees times pi over 180, which is pi over 3, right? And by the way, cos 60 gives half, cos negative 60 is also a half. So negative 60 or negative pi over 3 is another possible solution. Express f in the form or sin x plus alpha, where alpha is an acute angle. So we'll let cos x plus 2 sin x be equal to r sin x plus alpha. So we can expand the right hand side using the addition formula, the trig addition formula. So we have r, and then we expand the sin x plus alpha. So we get sin x cos alpha. And then we alternate. So we get cos x sin alpha. So we create now coefficient for the cos x and the sin x. So for the cos x on the left hand side it's 1. And on the right hand side, coefficient of cos x is what? What's beside the cos x now? Sin alpha. And don't forget the r. So it will r sin alpha. On the right hand side, coefficient for the cos x. And the coefficient for the sin x on the left hand side it's 2. And on the right hand side for sin x we have cos alpha. And don't forget the r, of course, outside. And now we can divide these equations by each other, right? So that's equation 1 and equation 2. So put equation 1 over equation 2. So we get 1 over 2 equal r sin alpha over r cos alpha, which is tan alpha. Because the r cancel, right? So, and sin over cos, that's tan. And on the left hand side we have 1 over 2. So tan alpha is equal to half. Let's write it clearer here. So it's 1 over 2. And we have r sin alpha over r cos alpha. R cancel r there. Half. Sin divided by cos, that's tan, right? So tan alpha is equal to half. So we can use our calculator to get alpha. And that should be 26.6 degrees. If I'm using 1 decimal place. So we can use Pythagoras theorem to get the exact value for sin alpha. Alright, remember tan alpha is opposite, tan is opposite over adjacent. It's 1 over 2, so opposite is 1, adjacent is 2. And we use Pythagoras theorem to get the hypotenuse, which is 5. Which means that sin alpha is opposite over hypotenuse, which is 1 over root 5. Good? Times both sides by root 5. Then r is equal to root 5, right? So we have alpha and we have r. So r, so right now our solution now. So r is root 5. So cos x plus 2 sin x is equal to root 5 sin x plus 26.6 degrees. Hence or otherwise, find the general solution of cos x plus 2 sin x equal to 0. So remember, cos x plus 2 sin x is root 5 sin x plus 26.6 degrees, right? So we equate that to 0. We want to solve now for x, so we can divide both sides by 5. By root 5, sorry. Divide both sides by root 5. Root 5 cancel root 5. Zero divided by root 5 is 0. So sin of what gives you 0? I want the general solution. So sin of general solution would be what now? N pi, or n, we can use 180. So x plus 26.6 equal to 180 n, right? So, and then we subtract 26.6 from both sides. So x equal 180n minus 26.6. The minimum value. Now remember, a fraction is at its largest, is at its smallest, it's at its minimum. When the denominator, it's at its largest, right? Now what value of f would make the denominator it's the largest? Remember the function? Alright, the maximum value of this function would be root 5, and the minimum value of this function would be negative root 5. Since the maximum value of sine is 1, and the minimum value of sine is minus 1, then root 5 and negative root 5 would be the maximum and minimum values of the function respectively. Alright, so which one will make the function larger, smaller, negative root 5, right? Because that would give us a very large denominator. Alright, so 2 over 2 plus root 5 is the minimum value of the function there. Because that's when the denominator is at its largest. Any other value will give us a smaller denominator. Hence a larger minimum value overall. Right. Next problem, prove the identity. So we can begin with the left hand side. So tan A plus B. Remember tan is sine over cos, right? So that's sine A plus B over cos A plus B minus tan A. So that's the left hand side. And tan A is sine A over cos A. So we can aim now, we're expanding there. So using the addition formula, expanding sine A plus B, we get sine A cos B. And then cos A sin B over denominator so we expand the cos there, we get cos A cos B minus sin A sin B over sin A cos A. Now we can bring the denominators together. So denominator is okay, just the numerator we need to worry about. Denominator is always a product. Two denominators there. And just realizing we didn't have to expand the denominator. It's really a numerator we have to worry about, right? So the numerator would be cos A times all the numerator there, all the terms here in the numerator for the first fraction. Minus sin A times all the denominator there in the first fraction there. Alright. So we put back a denominator. Cos A, and of course, what we have in the bracket here is really just cos A plus B, right? And the proof that we are setting out to prove, that's what the denominator is. So we just leave it alone and just try and fix up the numerator. So we'll distribute the cos A. Distribute the cos A here. We get cos A sin A cos B, right? So I'm going to distribute the cos A to each term in the bracket. And for the second term, the cos A and the cos A give us cos square, right? That's cos square A sin B. The other term now, we distribute the negative sin A. And then we'll have now plus sin square A sin B. So plus sin square A sin B. Oh, that cos B there at the end should be sin B. Soon change it. Notice in the numerator here now, some terms will cancel. The cos A sin A cos B, we have a similar term there. It's negative. The order is different, but the same terms, and it's multiplied, and its multiplication is commutative. So the R is the same term, so one positive, one negative, so those are deleted. So we're left with cos square A sin B plus sin square A sin B. So sin B, that's cos B, should be moved. So we put back the denominator, because the denominator is in the form that I want it to be. And now we have sin B as a common factor. So we can factor, yes, let's make the changes. So we can factor sin B, and then in the bracket we have cos square A plus sin square A is a Pythagorean identity we should recognize. It's equal to 1. So the bracket comes to 1. So it's really, the numerator is really just sin B. So the left hand side, so that's what we have on the right hand side, right? Sin B for the numerator, same denominator. So the left hand side equal to the right hand side. And our proof is complete.